Ever since we've been pointing spacecraft at the sun, 2 regions on our star have been missing from satellite images. The sun's 2 poles have never been mapped because all the solar images we've built have remained in the ecliptic plane, the swath of space roughly aligned with the sun's equator, where all the planets orbit. A new mission from the European Space Agency and NASA called Solar Orbiter aims to escape this plane and take the very first images of the poles.
The planets are all moving and circling the sun, and so we already have some velocity going one way. If we want to launch up out of the ecliptic, it requires more energy.
To get outside the ecliptic plane, Solar Orbiter uses Earth's and Venus's gravity to slingshot itself into a view of the poles. The only other satellite to fly over the poles was Ulysses, which launched in 1990 to study the solar atmosphere. But Solar Orbiter will be the first mission to capture actual images of this hard-to-reach region. Scientists think the poles could be the missing piece to understanding what drives the sun's activity. Every 11 years, the sun's magnetic field flips. North becomes south and vice versa. This mysterious process has direct effects on Earth. Before the poles flip, solar activity reaches its peak. The number of eruptions increases, sending powerful bursts of solar material that can potentially harm our astronauts and satellites.
We don't really have a good understanding of the global solar behavior.
Another one of the mission's goals is to monitor how these eruptions and solar material travel through space. Using a suite of 10 instruments, Solar Orbiter observes an active region on the surface as it explodes, and then also takes measurements as the escaping material passes directly by the spacecraft.
Solar Orbiter will give us a comprehensive, full view of the entire sun and how the sun is impacting throughout the entire solar system.
At closest approach, Solar Orbiter will be closer to the sun than Mercury, at a mere distance of 26 million miles away, the ideal distance to get a comprehensive view of the sun and its surrounding atmosphere. It will fly close to the sun every 6 months and endure temperatures more than 900 degrees Fahrenheit. To survive the intense radiation, a large titanium shield protects the instruments, while a carefully orchestrated dance of opening and closing eye holes in the shield allows the instruments to peep out at the right time. Other instruments will directly measure solar material from behind the shadow of the shield. All of these observations will tell us more about the sun than we've ever known before. And by the end of the 7-year mission, we will have seen our star in a completely new way.
Our understanding of the sun will change dramatically. I will say that we are living in a revolutionary moment in our field.